Okay, so let's get started. Good morning, everyone. Welcome to day 3 and final day of winter SAT+SMT winter school. It is very fitting that our speaker today, Professor Shavik Kai, is the Best Paper Award winner at SAT 2021 conference. Professor Kai is a professor at Institute of Software, Chinese Academy of Sciences. He received his PhD degree from Peking University with Distinguished Doctoral Dissertation Award. His research interests include constraint solving and combinatorial optimization. He has published more than 80 peer-reviewed papers in areas as artificial intelligence and software engineering. Perhaps more closer to us, his solvers have won a lot of medals at the SAT, SMT, and MaxSat competitions, and including as well as the Best Paper Award at this year's SAT conference. His algorithms have been prominently used in important real-world applications, including radio spectrum repacking, message scheduling, virtual machine pre-provisioning services, as well as in electronic design automation. We are very excited to learn about SAT solving, and especially a very interesting line of work that Professor Kai has pioneered and pushed for in the last few years. So over to you, Shavik.
Thanks. Okay. Thanks for the invitation. And this is a tutorial on SAT solving. I guess you have already heard many talks during this school. So that's a good news for me because I can count on the previous talks that you have already seen many basic concepts on SAT solving. Okay, I will start from 2 ways about solving problems with computers. One way is that when we face problems which can be stated formally, we state the problems using some mathematical languages, and then we develop efficient algorithm to tackle them. So typical scenario is theorem proving, okay? And on the other side, we have more and more learning algorithms come out. And these algorithms are aimed at solving problems that cannot be stated formally. So we feed the computers some examples and then train them to get a model to solve the next instance. Typical scenario is like face recognition. So about the first way, we usually refer to constraint solving because the core of this way is on the solving algorithm. The first part we call modeling, and in the SAT community, we usually call this part as encoding. Okay, we usually call this part as encoding, and the next part, and this is the solving. And we have many different popular mathematical languages to model our problems. And I list 4 popular languages here. The first one is Boolean algebra. So this is about SAT. We concern about the logical structure. And then opposite to the logical structure, we might concern more about numerical constraints rather than the logical structure. And if we take care of pure numerical constraints, this is mathematical programming. And on the other side, we have 2 generalized languages, the CSP and SMT. In CSP, we can define various constraints by just like some compilation. We can define constraints as we like. For example, we can define the all different, and this is about global constraints. And in this SMT, actually we take care about some restrictive form of first order logic, because generally first order logic cannot be decidable by computers. So we only take care first order logic with respect some certain background theory. So in this part, we have combined a logical structure with some background theory. Okay, so why SAT? SAT sits at the core of constraint solving. And as we know, it is the first NP complete problem, and it is very conceptually simple, and we can easily understand it according to its definition. Despite its simplicity, we have many important theoretical results. We have many important applications. And also, we have open source solvers. We have the codes. We have benchmarks on the SAT competition website. So that motivates more and more young people going to this community and contributes. So, and this SAT problem is also emphasized by several experts. For example, by Donald Knuth, and he, in his famous book, the series, The Art of Computer Programming, he wrote a vessel. He called it a vessel. Actually, it's a book about satisfiability, and he says that SAT problem is a killer app. It's a killer app because it is the key to solution of so many other problems. And also we have the Turing Award winner, Clark. He says the efficient SAT solving is a key technology for 21st century computer science. So this is some quotation. Now, this talk is about SAT solving because it's a tutorial. So I will try to cover different aspects of the SAT solving and algorithm. So I will begin with the basis about the basic algorithm and some hardness results we need to know. And then the second part is about encoding, because when we try to use SAT solvers to solve your problem, we need to encode the problem into a SAT format. So this part is about how to use a SAT solver. And then the following three parts is about the solvers, including the two popular methods, CDCL and local search. And the final part is about how to combine these two methods. Okay, the SAT problem, propositional satisfiability, or sometimes known as Boolean satisfiability, is defined as this. Given a propositional formula phi, test whether there is an assignment to the variables that makes this formula true. So this is an example formula. It's a propositional formula in CNF form. So SAT is a core problem in computer science and a basic problem in logic. And its powerfulness lies in two sides. In industry and science, the first way to use SAT is use it as a search engine to find a certain object. For example, to find a combination, to find a bug, to find a path. And okay, on the other side, we can use it as a prover. When we try to prove something is a tautology, we actually try to prove it that its negation is unsatisfiable. So the application of SAT solvers come from both these two sides. Now we see some basic concepts in the SAT problem. The SAT solvers usually adopt the CNF form, conjunctive normal form here. So this is a small example. And we have Boolean variables, x1, x2 to xn. And then we can define literal, which is a variable or its negation. And then we can define clause. A clause is a disjunction of literals. And usually we also write clause as a set of literals. For example, the first clause can be written in this way. And a CNF is a set of clauses. So the SAT problem is try to find an assignment to satisfy all the clauses at the same time, or prove that this does not exist. Okay, a truth assignment assigns a truth value, true or false, to each Boolean variable x. And if this satisfies a clause, if only if in the clause there is at least one true literal. And if all the literals in the clause are falsified, then this clause is falsified, or we say it's conflicting. It's conflicting. And we also have a unique clause. Unique clause means that there is only one unassigned variables in the clause, and all other variables are falsified. So for other remaining cases, we say a clause is unresolved. Okay, although SAT is generally NP-complete, some subclasses of the problem can be solved efficiently. Theoretically, that means that it can be solved within polynomial time. For example, 2SAT and HONSAT can be solved with a P algorithm, while some other classes are NP-complete, for example, 3SAT. So here is a small example of 2SAT. We can solve 2SAT problem easily by construct a graph in this way. Now we get a small formula of 2SAT, and for each clause, we have two literals. Then for two literals, for each of the literal, we make a node in the graph. And then for each clause, we produce two edges. For example, in the first clause, no x or y, then we have no x or y, then we have no x, that is x connected to y. Then we have this edge x connected to y, and the other way, no y pointed to no x. So this way. So this simply implies means that if for this two literal clause, one literal becomes falsified, then the other has to be true, because we must make every clause to be true in a model, in a solution. So for every two literal clause, we have produced two edges, two direct edges in the graph. Now, in the end, we construct a directed graph by scanning all the clauses. And then we check whether there is a variable x such that we can find a loop between x and not x, which means that we can imply something from x, and then finally it implies no x. So this implies that the formula is unset. And if the formula is satisfiable, we can just assign each variable step by step. For example, we can pick x and make it to true, for example, and then it will, according to the direction, it makes y to true, and then it makes z to true. So true is a assignment, is a satisfiable assignment for this formula. And then we are curious about, is there any criteria that allow us to distinguish between treatable or intreatable classes? And surprisingly, yes. And this is a very significant result obtained by Scaver in 1978. Loosely speaking, this dichotomy theorem states that every subclass of SAT can either be P or NP complete. That means that for every class that we can characterize by some constraints types, we can tell its in P or NP complete, and no other types, and not in the middle, something like that. And here he considered the Boolean constraint satisfaction problems, which is a general version of SAT. And a class of SAT is defined by a set of constraints C. So each set C determines a class of formulas such as 2 CNF, 3 CNF Hom formulas. Okay, now the theorem is like this. We have a Boolean constraint set. So this corresponds to a subclass of set, right? And this class is in P if it satisfies one condition below, at least one condition below, and otherwise it is NP complete. And here we list the four conditions. One, C is 0 valid or 1 valid. This says that we can assign every variable to all 0, and then this is a solution to the formula. And the 1 valid means that we assign each variable to true, and it's a solution to the variable. Okay. And the second condition, C is weakly positive. Weakly positive means it is a Hom cross. Every cross is a Hom cross. And a Hom cross means that every cross has at most one positive literal, and the other literals are all negative. This is the Hom formula. And we also have the weakly negative case. This corresponds to dual Hom formula. So they are just like symmetric. And the third case, C is bijective. So for the SAT problem, this means the two SAT problem. Okay, finally, the last case, which is not so familiar to solvers, C is affine, which means that these constraints corresponds to a system of linear equation. We can understand in this way, all the solutions of the formula consist of the solutions to a system of a linear equation, and this is a closed and this is a closed system. So two affine formula can be joined together to get another affine formula. Okay, and if a formula is not in these four cases.
Shall we? I believe this is linear equations mod 2, right?
Yeah. Yes. That's the same, equally defined. Yes. Mod 2. Yes.
Thank you.
In the Boolean field. Okay. Thanks. Now for the 3 set, the best known algorithm run in exponential time with the number of variables. So we did not find any better algorithm, which motivates the hardness assumption that maybe better algorithms do not exist. So let's quit to find a better algorithm. And there are 2 assumptions here. The first one is known as exponential time hypothesis, which loosely speaking, it means that 3 set cannot be solved in this time, 2 to small o of n. And the strong version of this ETH, SETH, means that we can't find a algorithm with this bound, where this star means that it suppresses the polynomial path. Okay, so we can't find an algorithm with the bound c to the nth power, where c is constant smaller than 2 for k set with large k. So this is quite negative results from the theoretical side. Okay, so for the theoretical algorithms, some researchers try to improve the trivial bound for fixed model, because for the general model, we have just seen that there are assumptions that we actually can't do better than the trivial bound 2 to the nth power, but we can fix some model. For example, we can fix random reset and we can find some improvements. And this one is found by scoring with a local search with a random walk algorithm. And also it can be combined with the PPSG algorithm, which is a famous algorithm in the theoretical line of SAT. And these two results it is state of the art in solving 3 SAT upper bounds. And for the deterministic algorithms, we can find the first case I just introduced is belong to randomized algorithm. And we have some skills to, for example, to randomize the random walk algorithm. And also we can have some exponential algorithms using some pruning technique. And this results to 1.5 to the nth power and 1.473 to the nth power. Okay, so these are the theoretical results of algorithm. And for a model like known as unique K-set, which means there is a unique solution in the formula in this model. And the current best algorithm is PPSG in 2005. Okay, and for the random case set, there is a very interesting phenomenon called phase transition. Okay, which is very similar to the phase transition in physics in our world. For example, in between water and ice, there is a very small area of the temperature that the water will quickly become ice. So for solving the random case set using DPLL-like algorithm, there is a similar phenomenon found. And here are two pictures. In this picture, at the top, this is the computational harness about solving the random case set formulas. And this is the ratio. When the ratio increases, the ratio is the number of crosses divided by the number of the variables. And this measures how many branches of the DP-like algorithms have occurred to solve this formula. So we can define there is a easy to hard to easy mode, and the harness area corresponds to the phase transition in random case set. So this random in the random case set, this phase transition says that when this ratio is small, for example here, when this ratio is small, then the formula is very sparse, right? It has small number of constraints, so it is usually satisfiable. And then when the ratio becomes larger and larger, suddenly there is a sharp area, and beyond this area, the formula becomes unsatisfiable, and this can be proved theoretically. And is there a critical point? Is there a critical point of the phase transition? Now there is an assumption that there is a critical point, but hasn't been proved exactly yet. So usually sits in the range of this range. And this phase transition is interesting not only because it is connected to the physics phenomenon, it also motivates the early development of incomplete solvers, because such formulas are very hard to solve by DPLL or CDCL solvers, even nowadays, because they are too I don't know, too random. So it's hard to reason about the structure. And also when it sits in the first transaction, the hardness is very high. So in about after 1990s and 2000 and about 2000, stochastic local search and survey propagation from physics are developed to find efficient algorithms to solve these paths of benchmarks. So we can, when we read the literatures, we will find that early works about incomplete algorithms, they focus on solving the benchmarks from this phase transition. And this is a very short introduction about survey propagation. It's derived from the cavity method for spin glasses in statistical physics. So basically, it's iteration algorithm. It is built to work on a vector graph. This is a vector graph, and the square corresponds to a cross. A circle corresponds to a variable. Now a variable is connected with a cross with a solid line if it's a positive literal in the cross, and with a dashed line if it's negative in the cross. For example, this V1, it's positive in cross 1, so it's a solid line, and it's negative in cross 2, so it's a dashed line here. And in each iteration, the variable will pass a message to the cross, and the cross will also pass message to variables. And this is a little complicated, which will not explain too much here. But finally, for formulas, for random Kaiser formulas before the first transition, it will converges to get the solution. Actually, the current best method for solving random satisfiable K-set close to first transition is to the combination of this survey propagation combined with local search. And usually, a survey propagation procedure is called to simplify the original formula because it usually failed before 4.2. We have this message propagation algorithm, but its converged condition usually is less than it failed before getting to this first transition about 4.2. But it can be used to simplify the formula, and afterwards we call local search to solve the subformula. And in this line, the current state of the art is built in, I think it's about in 2013, and can solve 10 million variables random reset near the first transition within 2 hours. Okay, now we have talked something about the SAT algorithm. Before we go further, we need to bear in mind that we are talking about, what are we talking about? Because in SAT, we can talk about algorithm, we can talk about solvers, but they are different in different contexts. For example, when we are talking about the algorithm, we try to find some better bound. We try to improve the bound. And when we develop solvers, actually, we can't theoretically prove the property of these solvers, but we use some heuristics to improve their performance, their practical performance. So there is a big gap between theory and practice, just like this joke here. And so for newcomers into this community, I guess the first question is, what is your interest? It's about the algorithm or about solvers? And many basic materials and many aspects are covered in this textbook, Handbook of Satisfiability. And now we have the second edition.
So shall we just, out of curiosity, on the previous slide, the quote that you put on the right, is that your quote?
This slide?
No, the next one. Yeah. So theory is when you know everything, but nothing works, and practice is when
Okay.
everything.
Yeah. Yes, I quote this joke just to emphasize there is a big gap between theory and practice. And we can't have both. Usually, we can't have both. Just a very few exceptions that is beautiful and practical. But most of the time, if we engineer a solver, we actually can prove its complexity. And if we try to prove some better bound, actually it does not work in practice. So this is a contradiction. And yes, and I remember when I attended the first SAT conference in 2009 or 10, then there are two groups of people in the coffee break, and one is about the theoretical and one is about solvers. But we rarely find these two communities to talk to each other. So, and I really think they should talk to each other. So the SAT revolution is about the SAT solvers. It's about using a SAT solver, using SAT solvers as an oracle to tackle the hard problems in other fields. For example, in physics, in mathematics, in hardware design. So this definition is taken from this article by Manai and Oliver. SAT solvers emphasize on the programs with practical performance. And now today's solvers can handle formulas with millions of variables, resulting in the SAT revolution. And if you are using SAT, you have a tool in your hand. And then when we face with a new problem, we can tackle this problem in 3 steps. First, SAT encoding, and then SAT solving, and then decoding. And if we just cared about solving the problem, we don't even want to open this part. And so the first part we need to do is the SAT encoding. And SAT revolution has touched many areas. It's a very important tool in the history of EDA, and also right now is many advanced EDA tools are built on the basis of SAT solvers, and also in program analysis. But in this part, SMT is more convenient. But we have to say the SMT also needs to call a SAT solver in its engine. And AI planning now, the SAT-based approach is still one of the popular approach for AI planning, and cryptography and mathematics and resource allocation and so on. So if we have a problem and we try to solve the problem using a SAT solver, then we need to express the problem in formats that can be accepted by SAT solver. Now, many SAT solvers adopt the DMAX format. This is the input file, and it starts with the lines start with a C are comments, so they will just be ignored. And there is only exactly one line start with a character P, and then follow with CNF, and then 2 integer numbers. This is the problem definition line, and this one is the number of variables, while the latter one is the number of clauses. And then following, we have many clauses. Each line corresponds to a clause and with a 0. So a negative number corresponds to a negative literal. So for example, for this clause here, we have x1 and no x4 and no x3, and 0 is the end. Okay, for the output format, if we find an assignment, we usually need to print it out. Now here we also have the comments line, which can be ignored. And we have a solution line. It can be satisfiable, unsatisfiable, or unknown, saying the decision result of the problem, followed with the V lines. V lines actually means the value of the value of the variables in the solution. And we can have many V line. We can also have one very long V line. That's okay, just depends on your habits. And in the end, it also ends with 0. And now for the unset, some solvers support the derived or direct proof format to support the proof. I guess because I have seen that another tutorial given by Manai is about this part. I guess he have shown you many aspects about this proof. Okay, now we go to the set encoding. I will give some examples here. The first example is a problem called graph coloring. This is a very famous problem in graph theory. Coloring is that we give a color to each point in the graph, to each node of the graph, such that if two nodes are connected with each other, then they should be assigned with different colors. And the graph coloring problem is to find a coloring for the graph that minimizes the number of colors. The decision version of this problem is that given a positive number k, and we decide whether a graph can be colored with k colors. Okay, so we look at the 3 coloring problem for a small example. Here is a very small graph here with 4 nodes, and we try to decide whether it can be colored with 3 colors. Now we need to use some variables for each node, because there are 3 colors. So we need 3 variables to decide which color it is finally assigned. X11 means that this node 1 is assigned to color 1. So if X11 is true, if this is true, that means that the first node is colored with this color 1. So now for this example, we have 12 variables in all. And then we produce some clauses to say that coloring is proper. The clause is produced to make sure that if two nodes are adjacent, then they cannot share the same color. Okay, let's take this edge, for example. Node 1 and node 2 are adjacent, so they cannot be colored to color 1 at the same time. They cannot be colored to color 2 at the same time. They also cannot be colored to color 3 at the same time. And for every edge, we have these clauses. And finally, we need to produce a positive k clauses to ensure that each node is colored. Because if we do not have this part, then we can simply put all the variable to false. But that does not solve the problem. They're just saying that we do not assign any color to any node. So we need to constrain that each vertex, each node must be assigned to a color. And this is guaranteed by a clause with positive k literals. And then we get all the clauses and hand it to a set solver, and we get the result here, which we can decode it to the solution of the coloring problem. We get the node 1 here, X11 is true, and these are all falsified. and the XTT is true, and this is true, this is true. So we know that the first node is colored 1, and the second node color 2, the third node color 1, and the fourth node colors the third color. Okay, the second example is a logic puzzle. We have many logic puzzles actually can be solved using set solver. So now if we know set solvers and how to call a set solver, actually we don't need to be very smart to solve the logic puzzle. We just need to encode them into a set formula. Now the question is, at least one of them speak the truth, and who speaks the truth? A says that B is lying, B says that C is lying, and C says that A and B are lying. Sorry. And when encode this problem to set, we need 3 variables, A, B, C, which represent A, B, C speak the truth respectively. So no A represent A is lying, and no B represent B is lying. Now we describe this problem in the CNF formula. The first clause says that at least one speak the truth, and the second pair of clauses corresponds to the sentence of A. A says that B is lying. So if A says the truth, then B is lying. So we have A implies no B. And on the other side, if A is lying, then B speaks the truth. So we have a pair of clauses here. And for the other sentences, we also have a pair of clauses for each of them. And this is not in the form of a clause, and we can just equally describe them in the form of clause. The result is that A is lying, B speaks the truth, C is lying. We can have more complicated example of logic puzzles. Just be and we can solve all of them if we can encode them into a set formula. Now let's solve another game called Sudoku. In this game, we are given a square with some cells. For example, here is a 9 times 9 grid, and in this 9 times 9 grid, we have 81 cells. Then there are some constraints. First, we need to assign to each cell a number, and to ensure that each cell in a row is different. Okay, and then for each column, we also need to assign the number 1 to 9. Each of them corresponds to a cell, and to make sure that they are different in the same column. And also we have a square for this 3 plus 3. And we need to also make sure that each cell, no 2 cells in the same square share the same number. Okay, in the beginning, the puzzle were given some initial assignments of some cells, and then we are asked to fill in the numbers to the remaining cells to make sure that all the constraints are satisfied. So we have 3 constraints: this row constraints, column constraints, and square constraints. Then to encode this problem to set, we first need to introduce the variables. We need a variable with 3 indexes, p with I, j, n. I means the number of row, the ith row, and j's column is filled with number n. Okay, for example, if p 1, 3, 9, this means that the first row and the third cell here is assigned with number 9. So if this variable is true, then it is assigned with 9. Then we come to introduce the clauses. First, we need to assert the initial value that is given. So for each one of the given value, we just give a unique clause. Okay, then we need to introduce clauses to make sure that every row contains every number. Okay, for this one, let's look at it. Let's first fix a row. For example, let's first fix I equals 1. So we see this part. And this part says that for each of the number n, it must be appear in at least one cell of this row. So it's like P1J. For example, when we care about n equals 2, then we get this J, which means that number 2, this number 2 must appear in one cell in the first row. And then when we conjunctive all of these clauses, we say that for n equals 1, n equals 2, and 3 to 9, they all must appear in a cell of this row. So this row have 9 cells, and here are 9 numbers. They all must be appear in this row. That guarantees our first constraints. And this is for one row. We just make a conjunction for all the rows. Then we cover the first type of constraints. And for the second type, it's very similar. For the second type, it's about the column. So it's very similar. We do not need to expand it. Now for the block constraints, we have additional indexes to identify which block we are talking about. So we have R from 0, 1 to 2 and S 0, 1 to 2. And this block is 0, 0, and this is 0, 1, this is 0, 2, and this one here is 1, 0, and so on. So this is talking about the block which we are talking about. And the remaining talks about in the same block, because we have 3 lines and 3 columns, and each number must appear in a cell of this, one cell of this 9 cell. So we have 3 times 3 cells here, and each number must appear in at least one of them. And when we conjunct with all the 9 numbers, we have described the case for one block, and then we conjunct all the cases about all the blocks. Okay, and finally, we says that no cell contains more than one number. Then we this part we go to the circuit. Usually, the SAT solver is seen as a basic engine in electronic design automation in EDA.
Shawe, I have one question about the slow encoding. So you showed one encoding, but I mean, there can be other encodings, and from what I understand, the performance of the SAT solver can depend significantly on the encoding, right?
Yeah.
So, so is the encoding that you showed, is that the best or one of the best for performance, or was it just to illustrate how an encoding can be done?
This is a direct encoding. And I do not say it's the best for CTCL solvers.
Okay. Okay.
Yeah.
So this is just one of the different possible encodings.
Yes. Yes.
Okay.
Mm-hmm. Yeah, and for the circuit, we need to encode each type of the logic gate to CNF form. So this is the cheating transformation. I guess it's very famous, and many of the speakers before have talked about it. Let's take one or two examples here. For example, C equals A and B. So now we realize that this is equal. So it's two sides. We have two, C implies A and B. Now this is not C or A and B. And we distribute it, we can get the letter 2, the clauses here. And the other side, A and B implies C. So we have not A and B, and or C. So this is no A or no B or C. Okay, so we have this as the first clause, and this 2 is the distribution of this clause. So we can transform the AND gates into 3 clauses. And now the no AND here is, well, it's similar here. It's very similar. Each of the gates can be transformed in this way, and it's a linear transformation, means the time and space are all linear. I can leave this for exercise of you guys if you are interested here. And when we can translate the circuit into CNF, we can try to perform some task about using SAT solving to solve the EDA problems. For example, there is a significant task in EDA called equivalence tracking. And in this problem, we need to decide whether the 2 given circuits, these are 2 circuits, N1 and N2, whether they have the same function, which means that for any input, they output the same. The output is the same. Then what do? We can combine the output of these 2 circuits with an XOR gate. Then if we find an input, know that here input is the bit, right? The Boolean bit, Boolean bit vectored here, the Boolean bit. And if we find a vector here as input to make that the XOR gate outputs 1, then it says that we find an input that N1 and N2, the outputs are different. So the XOR is 1. And now this corresponds to a circuit. And then we can transform the circuit to CNF as we introduced in the previous slide. Then we call a SAT solver to check. If it is set, that means that we find such an assignment that the XOR gate is outputs 1. Then we find a counterexample saying that these 2 circuits are different, are functionally different. And if we prove that it is unset, then we prove that there does not exist any assignment that max XOR gate outputs 1. So we prove these 2 circuits are the same, functionally the same. Okay, this is the case for only a single output. Now for multi-output circuits, it's very similar. We just need to combine the outputs by an OR gate, for each pair of the outputs of 2 circuits. We connect them by an XOR gates. And then for all these XOR gates, we combine them by an OR gate. So if at least one of them is 1, this OR gate will becomes 1. And the encoding is similar. If we find an assignment here to make this final gate 1, then we find a counterexample. Okay, so this is an example. I take it from Bill's slides. It actually tracks these two small circuits, whether they are the same. So these two circuits are connected by an XOR. And then we try to find an assignment that makes this to 1. Okay, so we have a unit clause here such that this final output is 1. And all this corresponds to the gate here by cheating transformation. And then we can expand this out as a CNF. Finally, we can have a CNF and call a SAT solver to solve this. Okay, and SAT solver found many applications in EDA. For example, another example is ATPG, which is to produce text pattern that to test the chip finally produced. Because after we design the chip and we will go to produce the chip, right? And even the functional correctness is granted or approved in the previous stage, but after the production procedure, maybe some other factors, for example, the careless operation or the quality of the materials will make some faults happen. And a very typical fault model is called staggered. In a circuit, a staggered fault is that a y here just lose function. It either staggered 1 or staggered 0. So if it's a staggered 0, that means that this line is just broken, it's damaged. Then for a circuit, if we want to cover all possible staggered faults, we need to check all the ones, right? And this is a small example. If we have a circuit for multiplication, for this 3 bits multiplied by 2 bits circuits, then we have 50 Ys here. So then totally we have 100 possible staggered faults, because for each line, it can be staggered 1 or staggered 0. Now we need to cover all 100 possible staggered faults. And this can be done by call a SAT solver. For example, if we want to check whether this line here staggered 0, then we also we design a 40 circuits and collect them by an XOR. So it's still the same. The equivalence checking of these two circuits. Okay, previously we introduced some examples of encoding problems to sets, but all of the examples are combinatorial. They do not involve the time. And now we see another example, sequential, which is sequential, the AI planning example, which involves the time during the game. And in this game, we see in the initial, we have some blocks here in some positions, and there is a worker. And the goal of the game is that the worker can move in each step. It can move 1 step, or it can push a box forwards 1 step. And finally, you need to push all the blocks to the goal point here, which is located at this pinpoint. Okay, we have two actions. One is push and another is move. And we can't pull the box. We can only push it and we can move. So the push operation will, before the push, it's in a straight line. Before the push, the worker is here, the box is here, and this is empty. So after the push, the box is here, the worker is here, and this is empty. This is a push. A move can be described in a similar way. Now for this game, we cannot encode the existence of a plane in general, but we can encode the existence of a plane up to some length. So this is a bounded length. And I just want to mention that actually the significant application of SAT to bounded model checking is just similar to this bounded AI planning. That we directly we cannot encode existence in general, but we can give a bounded length to the solution. And this example is taken from SAC lecture by Sings. And in this AI planning problem, we have a tuple. We have a set of multi-value variables. For example, in our example here, each position can be 3-valued. It can be either empty or box or worker. So it's multi-valued. And then finally, we will encode them into Boolean value. And then we have an action set. A set is a pair preconditions of the action and the effect of the action. The preconditions describe the conditions for the action to be allowed to perform, and the effect of an action describe the effects after the action is taken. Okay, so both these both precondition and effects are sets of equalities of the form. Actually, it describes some states. And then we have the initial states. We have the goal condition. Initial states says that says some value for some variable here. For some variable here, then it's initially a box or a worker, and then the goal condition. Now our task is to find whether to construct a CNF formula F such that F is satisfiable if and only if there is a plane of length K. To encode this problem, we need two kinds of variables. One kind to encode the action. Now we can see we have up index T here, which corresponds to the time or the step. So this is the method for encoding sequential involving problem. We need to consider the time. And AIT, if AIT is true, that means that at the time T, we take action AI. Also, we have variables to encode the states. For each variable X, each variable X actually is a position. We need to consider at time T, what is its stage, what is its state. So now here, for example, in this small example, we consider, for example, x1 to be the first cell. Then x1 could be a worker, could be a box, and could be empty. And now T, if we limit T to be length K, then we need to consider T from 1 to K plus 1. This K plus 1 is because when we take K actions, we actually come to the time of K plus 1. Now in total, we have so many variables. And we need A kinds of clauses, actually three pairs, three groups. The first group says about the initial and the goal. And the second group says each state variable has at least one value and has at least one value. That means exactly one value. Each state variable exactly one value. And then this group is about the action. If an action is applied, it must be applicable. So this one says something about preconditions. And if an action is applied, its effects must be applied in the next step. And state variables cannot change without an action supporting this change. And finally, at most, one action is used in each step. For the first group, it's very easy. So just some unit clauses to state the initial states of the variables and the goal we need to touch. This part is also very easy. For each state variable, we has at least one variable. So we can get this clause. We get this clause to say the at least one. And at most one, we just take the negation between each of the two states to the same variable. That means that at any time, the variable cannot be assigned to two different values. So it's very easy to understand. And if an action is applied, then it must be applicable. This guarantees that preconditions must be satisfied if an action is applied. So it's a necessary condition. If A is applied, that means that the precondition of A, this must be true. Okay, so and what is this? Actually, this is a series of the states. So eventually, this comes to no A or followed with some positive literals describe about the precondition. And if an action is applied, its effects must be applied in the next step. Okay, and this part means that if A is applied, then in the T+1 step, all its effects are already in the true state, and its encoding is similar to this one. Now we get to the most difficult rule about the state variables cannot change without an action. This says that if for some state variable x, it is not equal to v at time t, but then at t+1, it becomes v, which means that something must happen between t and +1. Something must happen at this time t. So some action supporting this x to be v must happen. Now, if we write this, actually we if x not equals v at time t, so x, this is not at time t, and then s equals to v at time +1, then there must have this action. This action, at least one of them must be happen. So this is the action. And then we can describe it in the form of clause. We can get the negation here and all the action here. Finally, we get this clause. Okay, the last one is easy. At most one action is used in each step. So we just need to produce a two negative clause to say that no two action at the same time. All right. So we just finished the encoding part. We still have half hour for the first break, right?
Yes.
Okay. Now we get to the solving part. I guess many of you have already know this picture because in SAT solving, SAT is a logical problem, so we can use some logical reasoning to reason about the values of the variables. And the main method for tackle such combinatorial problems is to use search, either backtracking search or local search. We can, roughly speaking, we can divide the SAT solvers into two types, the complete solvers and incomplete solvers. For complete solvers, for the word complete, it means that when the algorithm terminates normally, then it will eventually decide yes or not for the formula. But that does not guarantee the time to terminate normally. And for incomplete solvers, usually stochastic local search, it is biased on satisfiable side. It can only be used to find a solution. If it cannot find a solution, we also cannot say anything about its unsatisfiability. So we have these two kinds of solvers, and I will, in the following, will introduce these two kinds of solvers. In the very beginning, as SAT is a logical problem, we can use logic reasoning to solve this problem. And the typical one is to use a resolution. A resolution says that if we have two clauses which has exactly one pair of complementary literals, for here, positive x and no x, then these two clauses imply new clause, and this new clause is called a resolvent of the clauses, which is the disjunction of the two original clauses except the pair of the complementary literals. And with this resolution rule, we have a saturation algorithm here. In each step of the algorithm, it finds all the pairs of clauses that can be resolved, and then add the resolvent to the formula. And this will be performed iteratively until no more new resolvent, no more new clause can be produced. And when the algorithm terminates, if there is an empty clause in this formula, then we return unset. Otherwise, we return set. Of course, this algorithm is sound and complete, but it has exponential time and space complexity, and particularly the space complexity is exponential and very high because in each step it generates all the possible resolvents. Although the saturation algorithm is not practical, but the resolution rule here is currently used in many solvers, actually in almost all of them, and direct use of resolution is in pre-process to use the resolution to simplify the formula. And this is done by each time we just consider one variable. Given a formula f and a literal a, we can, this is a variable a, we can simplify the formula by adding all resolvents about this variable and then removing all clauses that contain A or no A. Let's look at an example. Here is a formula. Then if we try to eliminate a variable E, this variable, then we can do all the resolution about this variable E. We can find E appears in this clause, and this two. And in the first two clauses, E is positive. In the later two clauses, E is negative. So we have a cardinality set about these two sets of clauses. Then we have the first clause connected with this one and connected with this one. And the second clause also can be connected to this one and this one. Then we have four pairs of, we have four resolution, which generates four resolvents. The result is here. And we add all the four resolvents to the formula and then remove all clauses contain E to obtain this formula. So we just remove the one variable from the formula because all its effect has just been found out by resolution. And in the real processes, this is usually used by the bounded variable elimination because we do not necessarily simplify the formula by doing this resolution. Sometimes if we do the resolution, we can introduce many clauses and this number can be bigger than the number that we removed. So the bounded variable elimination considers only the good cases, only consider if a variable, if the resolution on a variable do not increase the number of clauses, we perform this pre-process. And a special case of resolution is unit propagation. This is a standard technique in nowadays set solvers. A unit clause is where all literals are falsified except one unassigned literal. So unit propagation is that for the unit clause, it must be true. This literal must be assigned to be true to satisfy the clause. Otherwise, the formula is unset. Otherwise, the assignment cannot set the formula, right? So if we get a unit clause, for example, here originally x1 is a unit clause, it must be true. And if x1 is true, then this clause is satisfied. And then we removed all the no x1 from all the clauses. So the formula is simplified as this. Now no x2 and no x3 becomes unit. Then we can continue to do this unit propagation. We can continue to do this by assign x2 to false and to simplify the formula again, and then to assign x3 also to false and simplify the formula. And when we do this until there is no more unit clause, this is a procedure of unit propagation. In 1960, Davis and Putnam, they considered the question that can we do better than the resolution? And they proposed an algorithm called DP algorithm. Actually, the DP algorithm could be seen as a variant of the saturation algorithm, the very old saturation algorithm, but they add three rules. The first one is unit propagation, and the second one is pure literal elimination. This rule says that if a variable appears only positive in all the clauses, then it must be assigned to positive. And also similar, if the variable appear only negative in other clauses, it appears, then it must be assigned to false. The third rule says that each time we do not perform resolution on all the possible pairs. We just take one variable and do all the resolution and remove that variable. So in each iteration of the DP algorithm, it applied these three rules, giving the priority to rule 1 and 2 and then 3, until no further rule is applicable. This is the first effort to make a practical SAT solver. So from this DP algorithm, I was thinking solver is more like something algorithm and heuristics, because the framework here is somehow modified from the situation about resolution, but it introduced some rules about the unit propagation and resolution at one variable at a time. So when we use these heuristic rules to modify the algorithm, we get a solver. So I usually understand a solver as an algorithmic framework and then some heuristics in it. You will see in my following introduction, I will also introduce CDCL as this favor. Now, after DP, after the introduction of DP, there are many efforts focused on improving the SAT solvers. And there are two lines, the complete line and incomplete lines. In the complete line, we have DP and then evolved to DPLL in 1962. And then there is a period of history focused on resolution techniques. In 1989, Starmark's algorithm is about different level of resolution. And then in 1996, the significant breakthrough, the CDCL method is invented. So after that, many improvements have been made to improve CDCL, including the G-trap and trap about the data structure and various ideas branching, and Miniset, then glucose about the cross management, and then recently the co-Miniset PS, the Maple, Calical, KeySet. And also there is a branch about complete solvers about which is called Look Ahead. It also starts at 1996, and then there is a famous solver called Match, which is developed by Manai in 2003. And in the incomplete line, it begins about 1992 or 1991, which is the famous algorithm GSAT is designed by Selman, and a similar algorithm also designed by Gu Jun. And then in 1996, another famous algorithm called WalkSet, is a random walk style local search, is introduced. And then we have the novelty, which is a variant of WalkSet, and many variants of novelty have been introduced in these several years. And then we have G2 WalkSet, which is which proposes a concept called promising decreasing variable. Then after 2010, we have the so-called modern local search. We have set time proper set, CCS set, YAR set, CCNR. And another line of incomplete solvers is the SP algorithm. And we also have a line about hybrid solvers, which combines the complete and incomplete solvers to develop more efficient solvers. The challenge about hybrid solvers is proposed at 1997 AAAI conference, and after that, different methods have been proposed, trying to develop hybrid solvers. Personally, I would see this history as 3 stages. in the early stage, before 1990, it is an early stage, and the typical success is DP and DPLL and style marks. And after entering 1990s, both complete and incomplete solvers enter a booming stage. We have CDCL, we have the first local search set solver, and then to about 2010, the CDCL has gone to glucose, which is quite modern and has many is already have many successful techniques in modern time in this glucose. And then after 2010, we have complicated more engineering aspects. So it's not about the main principle or about the algorithm, but there are many heuristics, many engineering aspects in the solvers, trying to improve the solvers by these engineering aspects. And then in the incomplete line, after 2010, we have the so-called the modern local search. We call it modern because this local search can perform competitive on some structured formulas. So this is my personal view of the SAT history. And the current state is a SAT solver regularly can solve formulas with millions of variables within 1 hour. Now, before we introduce the main approach, CDCL, we first describe the DPLL algorithm, which evolved from the DP algorithm 2 years later. And this DPLL, the 4 letters, represents these four people. They developed this algorithm. The main feature of DPLL is chronological backtracking plus the unit propagation and decision heuristics. So DPLL, different from the DP algorithm, it's a search algorithm. We know that DP algorithm is a resolution-based. It's a resolution-based algorithm. In each step, it takes a variable and do all the resolutions about that variables, and then remove the variable out of the formula. So in each step, they reduce one variable from the formula. And this is a resolution-based algorithm. But coming to DPLL, it becomes a search algorithm. In the original formula, it can be split to two cases, actually two sub problem. In the one branch, if we pick a variable and split the problem to two cases, the variable can be assigned to 1 and 0, and then we condition the formula on this assignment. Then we get two sub formula, right? And this forms two sub problems, and then this can be iteratively can be splitted. And if for at least one of the subformula, we find a model, we find a solution. For example, we find a solution here, then we can find a solution to the original formula. But to improve unsatisfiability, we must prove the other branch does not exist satisfying assignment. Okay, so this is a typical backtracking framework of DPLL. And then in the history, we have all right, we introduce a concept about decision level, which is important in DPLL and CDCL. The decision level describes in which level a variable is assigned, either by either by decision heuristics or by UP. And originally we are in level 0. And then if we have unique crosses in the original formula, we can do some UP. This happens at level 0. And then we pick a variable to decide. We pick a variable and decided to assign 0 or 1 to this variable. This is a decide operation. And each decide operation begins a new level. So for example, in this example, we have 7 clauses. In the first step, we pick A and assign it to 1. So this begins a new level 1. And after decide a variable, we check whether there is some unique clauses. If there do exist unique clauses, we do the UP. So this is optional, and this is optional. If there is unique clauses, we do all the UP. But if we decide a variable and no unique clause appear, then we will decide another, and this begins another level called level 2. So this is the procedure of DPLL. The algorithm performs between decision and unique propagation. Okay, we run a small example here. We have this clause, 7 clauses, and at the first step, we assign A to 1. We assign to 1, so this is satisfied, and this no A is eliminated. And then we do not see any unique clause, right? So we pick another variable, say B, and assign it to 1 also. Then we satisfy this clause. Also, we do not have any unique clause. Then we continue to pick C and assign to 1. Nothing happened. We continue to pick another variable. This time is X. And in the first branch, we assigned it to 1. So this is satisfy, and no X is eliminated. Now we have a unique clause. Y, right? So X, so this branch implies that Y must be 1. Then we use a square to show that Y is implied. So Y is implied to 1, and then we also have Z. If Y is implied to 1, then we have, this is a unique clause, and this is a unique clause. But these 2 clauses can produce an empty clause, right? Because G must be true and G must be false, so we have a conflict here. Then we backtrack. To do X. The second branch of X is assigned to 0, and then we have a conflict here, and then backtrack to C, and then backtrack to B. When we finish the second branch of C, we backtrack to B. So this is a traditional backtracking framework and how DPL works. But in about 1990s, some people found that a back jumping technique from other fields, from like CSP, from the CSP algorithms, can be also used to improve DPL algorithm. When they check the backtracking of DPLL, we realized that, for example, after we check all the branches of X, then we need to backtrack. But we found that these conflicts in the branches of X involve only A, X, and Y, and they do not involve B and C, which says that no matter B and C are no matter what values B and C are assigned, if A, X, Y, Z assigned in this way, they must lead to a conflict. So it is meaningless to backtrack to C and B. Then we can, after checking all the branches of a variable X, we can directly back jump to the level before B and C. So this is back jumping, also called non-chronological backtracking. And in this way, the search tree is changed. You can see we directly go to this the first level, and then we check the second branch of A and directly find a solution. Okay, those are the early improvements to DPLL. And in 1996, the famous CDCL, which is the basis, the method of current modern SAT solvers, was introduced, and this is based on the concept of implication graph, because you want to learn something in conflict. Then, for the convenience, the algorithm maintains an implication graph during the search. In this graph, we have vertex edge. A vertex describes the information about a variable, including its value and its decision level. For example, in this formula, we have 6 clauses, and this note here, x31 equals to 0 at level 3, means that x31 is assigned to 0 at the 3rd level. And then the edge is the reason. It's the reason of variable assignment. And here, this note here, x2 is assigned to 0, but it's implied not by decision heuristics. x2 must be 0 because once these two values are assigned, then by the first clause, we have a unit propagation to, then we get x2 must be 0. So this is the first clause. And if we assign x1 to 0 and x31 to 0, we get a unit clause, no x2, right? So x2 must be 0. And this is at the level of the largest level of the clauses. Now, in this way, we can construct an implication graph during the search. And this graph is very critical for CDCL. Before we go to the details, we can give an intuition about how this graph is important. So here finally we get a conflict here, and this conflict is implied by the previous assignment. This conflict is implied by x5 to be 0 and x6 to be 0 at 5. Okay, if x5 is 0 and x6 is 0, and this becomes a conflicting clause. But how comes x5 to be 0? It has a reason. Then we can find a reason here. And similarly, we can find a reason of x6 to be 0. This is the reason. And if we think it this way, if we make a cut, for example, we cut the reason to get these two assignments, then we will not go to the conflict, right? Because this is a directed graph. If we make a cut here, for example, this cut made here, if we can ensure that the algorithm must consider this cut, then it will not go to this conflict. So we need to describe this cut. How to describe it? We can we can see there are two ways. For one way, we can see the nodes. The source of this card is x4 equals 1 and x21 equals 0. So we must assure that x4 equals 1 and x21 equals 1 does not happen at the same time. And if we can guarantee this, then it does not go to the conflict. And this equals to cross in this way. Okay, so this is one way to understand the implication graph. If we make a cut here, we will not go to the conflict. And this cut actually can be described by a cross. And indeed, this cross is the length cross in the following slide. And we can make different cut. We can make a cut here. We can make a cut here. Each cut corresponds to a cross that guarantees some forbidden paths, guarantee a cut.
Shall we?
Okay.
We were planning to have a break around this time. Do you think?
Okay, sure. Yeah.
I mean, perhaps you think we can have a break in 5 minutes, or you want to stop?
5 minutes or?
So we wanted to have a 15-minute break. It was originally planned about 15 minutes ago. So we are past 15 minutes.
Okay, yeah. So we can have a 15 minutes break.
You want to stop here, or maybe you can complete the next slide and then we can take a break?
No, I can just, this is a good point. This is a good point. It's about the intuition, and then I will go to the technical part. Okay, so we stop here?
Yeah, okay, cool.
Okay.
Let's take.
Okay. Now, previously, we just see the implication graph, which is very important in CDCL. And we have already seen its intuition, right? It has a trend in trends. It has this reasoning network and lead to a conflict. So the CDCL stands for cross-driven cross-learning, conflict-driven cross-learning. So the so-called cross-learning means to learn something from the failure, from the conflict here. So the intuition is that we make a cut from this reasoning edges, then we learn across. Now we go into the detail of the implementation. In the previous slide, that is an intuitive picture. So we can see that we have some information at each node, right? We have the value of a variable and the decision level, and we have a clause which is associated to an edge. But in our codes, in the implementation, we need to organize this information to some data structure. Specifically for each variable x, we use vx as its value, the value under the current assignment. And we have delta x, the decision level. And we have alpha x, which is the reason clause. If the value of the variable is implied, then it has a reason clause. And if the value of the variable is picked by heuristic, then we can see that its reason is just denoted by some special number. And now we can organize the picture in a clear way to help us understand the level. In this, we run a small example. In this formula, we have 6 clauses here. In the beginning, level 0, in the beginning, we check is there any unit clause? No, then nothing happened. Level 0, nothing happened. And then go to level 1, we pick a variable, say h. say H, and assign its value to 1, then what happens? We check and did not find any unit clause after this operation. So we do not have a unit propagation after this decision. Then we go to level 2. Level 2, we pick another variable, say B, and we also assign its value to 1, and its decision level is 2, and the reason is empty because it's not implied. And after level 2, we did not find any unit clause, so we continue to pick a variable to assign. In level 3, we pick Y, and Y is also assigned to 1, and also we did not find any unit clause to propagate. And then we go to level 4, and pick variable A assigned to 1, and we record the decision level of A to be 4. After A is assigned to variable 1, we have a unit clause. This is by implied by A and B's value. When A is assigned to true, B is assigned to true, then the first clause becomes unit clause, right? Then we can imply that C must be 1. So we have this C, the value of C is 1. And now here, the important thing here is that the decision level of C is the same as A. It's the same as the largest level of between A and B, between the reason. And it's the reason clause of variable C now is recorded as clause C1 because C is implied to the value of C is implied in this first clause. So we record its reason clause here. We record its reason clause here. And then we can continue to have this D because for the second clause, when A is assigned to true, then D is also a unit clause. Then D is also implied to 1, and the decision level is the same as A. Decision level is 4. The reason clause is C2 because it is a reason in the second clause. Then after C and D is implied, they together in the third clause, they will make the third clause become unit. C and D all assigned to true, so they eliminated from this clause, making the clause 3 become unit. So this implies that variable E must be 1. Okay. Then the decision level of variable E is still level 4 because both C and D are at the decision level 4. So it's variable E. And we continue to do this until we get the conflict. And now after we get the conflict, we already get this data structure. We already get this table. In the following, we are going to make use of this table here to do the conflict analyze, to learn a clause and to do the back jumping. Okay, let's see how it works. To analyze the conflict, first we need a queue, a first in, first out queue, starting from the conflict. So at first, we try to analyze this conflict. We try to analyze the reason that leads to this conflict. Then we can find its antecedent. That is the reason clause is C6. It's the sixth clause, this one. And the reason in this C6 is about F is variables F and G. So we pick we add F and G into this Q because the reason to this conflict happens in clause C6, and clause C6 has these two variables. So both variables must be analyzed. Then we go to this a new step. In this new step, we have variables F and and variable G. And in the first out function, we take F to analyze. Okay, we find the reason clause of F. We can find in this table. The reason is the fourth clause, right? So the reason is this clause, is the fourth clause. And here we find a recorded list, recorded literals. What is this? And in this term, in the clause C, any literals assigned at decision levels smaller than the current one will be added, recorded as the clause being learned. So in this clause, we have H. We have variable H. Its decision level is smaller than F. So H, the literal here, no H is recorded. What about no E? It is not recorded because variable E and F, they are at the same decision level. Okay, so in the implementation, that's what we do. When we go to this F, we find the clause, and in the clause, any literal that decided any literal that assigned at the levels smaller than this current variable, then we add it into the clause being learned. Okay. Now and for the other parts, for this E, it is not recorded. Instead, it must be analyzed. So we add it to the Q, to this analyzing Q. Then in the next iteration, this Q becomes G and E, and we have recorded literals, no H. Then we continue to analyze the variables step by step. In each time, in this time, we get the top of the Q, which is variable G, and then we check this table. We found that the reason clause of G is the fixed clause. In this fixed clause, we do not find a literal to record, and then we analyze E. And we also, in this clause, we do not find anything to add to the Q. Okay, because G and E also already appear in this Q, so they both have been analyzed. They do not need to add it to the Q at this iteration. Now the Q only has one variable, E, and at this point, we say this is a unit implication point, UIP. Okay, because the reason now at this Q we need to analyze becomes just one variable, which corresponds to a dominator in the graph, this variable E here. To get from the beginning to the conflict, we must somehow from the beginning to the conflict, we must pass through this variable, this node here. So it's a dominator for this graph from the beginning to the conflict. And this is a very important concept in the cross-analysis, because the popular method is that once we meet UIP, once we meet the first UIP, then we stop the analysis. And this E is recorded, then we stop. And also, actually, if we do not stop at this UIP, we can continue this analyzing procedure step by step until it touch the root of the reason. And we can stop at any stage which corresponds to a different cut. We can stop here, we can stop here, we can stop here, right? We can have many ways to stop the analyzing. And modern set solvers usually use the first UIP heuristic to stop this analyzing procedure. Now, after we get the learn clause, in this example, when we meet the first UIP, we stop this analyzing procedure and we get no H and no E, right? And after this, we need to backtrack. How to get the level of the backtrack? This can also be done by. Oops, sorry, I skipped one slide. Here the conflict analyze here also corresponds to a resolution procedure. Now we learn the clause no H and no E. It corresponds to a cut here. And this analyzing procedure can be also implemented by resolution steps. We see here the reason clause is about C6, C4, and C5. And this C3, we did not analyze it because we stopped here. We stopped here. So this C3 is not analyzed. Then in the analyzing procedure, the related clauses include C6, C4, and C5, right? And another way to get the learn clause is to make resolution among these three clauses. So we can make a resolution between C6 and C5, and then make this new resolution among the new clause and C4, and then we get the same clause. So if we look at this picture, look at the implementation graph, that's when we make a cut here, the related clause is C4, C5, and C6. And then we do the resolution according to the reverse order of this conflict, this implication graph. Then we will also get a learn clause in the with the same one we obtained. And then these are two ways to implement to get the learn clause. After we get the learn clause, we need to decide which level to backtrack. Okay. Now we continue to begin with this learn clause. We get the clause no H and no E. Now which level to backtrack? Now the current level is decision 4. And in this learn clause, we exactly has one literal in the current level. The no E, this no E literal. So it will backtrack to the level of the largest level of the remaining variable. And in this clause, we have only one remaining literal, no H. So it will backtracks to level 1. And in level 1, together with this new clause, we quickly imply that because H is assigned to true, so we quickly assign that E must be assigned to false. If we learn the clause in another way, we do not stop at the first UIP, we go further. And then we learn this course, no H or no B or no A. Okay, what about this case? Which level to backtrack? The principle is the same. We find the current decision level. The current decision level is 4, and we have the literal A. No A is on the current decision level, and for the remaining literals, we backtrack to the largest level of the remaining level. And here, H is at level 1, and B is at level 2, is in the second level. So we need to backtrack to the largest of these levels. Then we backtrack to level 2. In this case, we backtrack to level 2. And when we backtrack to level 2, we will redo all these variables, right? Because they are assigned after level 2. And when we backtrack to level 2 here, all the levels after this will be related to this conflict will be undone. Then at this level 2, together with this new clause, we will imply A must be assigned to false. Okay, so H, B, and this can be done by unit propagation. All right, so the previous 2 slides shows the technical parts about the conflict analysis. Now this is a complete example because here we only see one conflict analysis, but now here we get a small example that we have seen before to show that the conflict analysis in solving the formula in a complete procedure. Okay, the left hand side, the picture left hand side is the case for DPLL, chronological backtracking. Okay, then with this conflict case, conflict analyze, suppose in here, in the first conflict, we do a conflict analyze CDCL. Now we stop at the first UIP. And this is the first UIP. This Y equals 1. This is the first UIP, and we stop here. And we're using the same method that we mentioned before to learn the clause, no A or no Y. Now we need to backtrack, because now this Y is the current level, so we backtrack to the level of A. So after learn the clause, we directly backtrack to here, to the first level, A. And then we, here together with the new clause, we do a procedure of unit propagation and lead to the conflict. Once A is assigned to 1, together with this learned clause, we have Y must be 0, X must be 0, and then this leads to a conflict that Z must be 0 and 1 at the same time, so conflict. Okay, so the branch of A assigned to 1 can be cut. Now we get to the second branch of variable A. A is assigned to 0, and we quickly find a solution. So the conflict analyze, and together with the back jumping, we will change the search space, the search tree like this, and many subspace can be pruned because of conflict analyze. And this is the power of CDCL, the main power of CDCL. Okay, then after we introduce the key concept of CDCL, we now are ready to see the framework of this algorithm. This algorithm have two components, two core components. The first part is analyze conflict, the conflict analysis. In this part, we analyze the conflict, we learn the clause, and maybe we simplify the clause. And after we learn the clause, we do the non-chronological backtracking, just as we said. And besides, another part is the decision part. In the decision part, we need to take a variable to branch. We need to assign it a value that to start a new branch. So this is the loop of the CDCL. In each step, if there is in each level, we start with define a new variable, right? And after define a variable, if there is something, some unique clauses, then we do the unit propagation, which is also known as BCP. And this after the BCP stopped, if we go to a conflict, if this leads to a conflict, then we analyze the conflict and we backtrack. If the backtrack tells us that the whole space is traversed, has already been done, then we can output the unset because we did not find any solution there. We find the proof. But if the backtrack does not backtrack to the top to the negative level, then we continue. If backtrack to this level, we continue to do the unit propagation. Together with the learn clause, we can do a unit propagation. And if we in a stage we cannot do unit propagation, it will go to design another new variable, and then this is the loop. When the loop touch a leaf, that is the complete assignment, all variables are assigned, then we get the solution. This is the pseudocode of the CDCL framework. Okay. In the beginning, at level 0, we do the UP if possible, and then we go into the loop. So in each level, we pick a variable and its value to branch, and then we do a procedure of unit propagation. Okay, if this leads to a conflict, we do the conflict analyze, and then backtrack and continue. But this is just the framework, and we need many heuristics to make this algorithm efficient. Besides the cross-learning, we also have cross-management, lazy data structures, restarting, branching, and phasing heuristics, and something others heuristics to make CDCL solvers powerful. Now we are going to see the heuristics in the CDCL algorithm. The first one is the lazy data structure, which is also known as watching literal. Because the UP procedure, when we profile the program of SAT solver, we will find that actually most of the time is occupied by the UP procedure, nearly more than 80% or even 90%. So we need to find an efficient way to implement UP. A naive way is that every time we assign a new variable, we scan all the clauses where this variable appear. Then we scan all these clauses to check whether they become units. But this is very time consuming. And also when combined with backtrack, we need to modify a lot of information in the backtrack procedure. In about 2000 and 2001, a technique called watch literals is applied to CDCL. And in this technique, for each non-satisfied clause, we pick two literals to watch it. For each clause, we pick two non-false literals to watch these literals. And then we maintain, for each literal, we maintain a list where we maintain a list of clauses where the clauses that this literal watched. And then we update this information. So how can we find a unique clause? We can find if the two watchers, if the two watch literals, we did not find any new candidate watching literals, and one of the watching literal become false, then we know that this clause becomes unit. Okay, so the intuition is that if we pick two non-false literals here, and if they are not touched, then this clause we do not need to check it, right? Because it has at least two unassigned variable in the clause. So it must not be unit. Until one of them is touched, then we try to find another unassigned variable in this clause. If we can find another one, then we set it to the new watcher, and then we have still two watchers. So we know that this clause is not unit because we have at least two unassigned variables. So this is the intuition. Now, what we need to do is to maintain the information for each clause and maintain the list for the literal. So pick this clause, for example. If we at level 2, and we pick literal A and literal F to watch this clause. And suppose at level 3, this F is assigned to false. This literal becomes false, okay? Then we need to pick another literal for watching. And the way is to check backward. It scans backwards to find a new literal to watch the clause. And we quickly find that this literal G is a new literal that can be set as a watcher. So here, at this step, the two watchers becomes A and G. Okay, then suppose at level 4, G is also falsified. Then it tries to find a new literal to watch and cannot backwards H, no, and to the end, then it return to the beginning of the clause and then continue the search. A is already a watcher, so skip it. Then B and C is no candidate, then move to D. So now at this case, the two watchers become A and D. Okay, in this way, we can maintain the two literals. And suppose at some step, we find that we cannot find a new watcher. All of them have been falsified. Then we know this clause becomes unit. And after backtracking, after we backtrack to some high level, the two pointers do not need to modified. So this is a very efficient procedure. At the time of its publication, this shows a 10 times speed up to the CTCL solver. So it's very important. And okay, now we go to the second part of the heuristics, the branch heuristics. In each step, we need to pick a variable to assign a value so that we start a new branch. Then we have various heuristics for doing this. In the early days, we have static branching heuristics, for example, some special order. Then people develop dynamic branching heuristic, considering current partial assignment. For example, considering the literal sum, the frequency. And then going to the dynamic heuristics, considering the length crosses. For example, an important heuristic is VSIDS, and its variance about this VSIDS, NVSIDS and EVSIDS, especially this exponential VSIDS proposed in Miniset is a very popular one in modern CDCL solvers, and I will introduce later in the detail. And in 2004, we have another VMTF, variable move to front. So this is different from VSIDS. And also reinforced learning-based branching heuristic includes CHB and LRB. LRB is improved from CHB. And in recent years, we see that some dynamic switching between multiple heuristics. For example, in KeySat, in this year's winner KeySat, is switching between CHB and VSIDS by some heuristics. Okay, now I will introduce these three highlight heuristics in detail. The VSIDS is proposed to promote conflict faster. So this is the intuition of VSIDS. It compute a score for each variable and then select the variable with the highest score. Now, because you want to promote the conflict earlier, so this score is related to the possibility that a variable can cause a conflict. So because this reason, in every time the algorithm meets a new conflict, the score of all variables in this conflict is incremented, because they believe that if a variable participates in a recent conflict, then it is likely that it will cause a conflict in the future, in the recent future. So when the algorithm encounters a new conflict, then the score of all variables in this clause is increased. Also, periodically, the algorithm need to forget the previous effects, because if the search is long, then the scores incremented in the early history cannot be considered as important as the recent conflicts, right? The algorithm do this by dividing all scores with a constant periodically. Among the variants of VSIDS, the most popular one is the exponential variant. The first time proposed in Miniset, and here is the rule. Here are the rules in this EVSIDS. The score of some variables are bumped, actually is increased with a constant, and then this constant decays after each conflict. In the beginning, all scores are initialized to 0, and this bump score is default to 1. And after each conflict, this increment is divided by decay, and this decay factor is 0.5. I try to explain this because we want to emphasize the recent conflict, right? So in this way, this ink by multiply a factor bigger than 1, it is important than the previous ink. Okay, by doing this, it emphasizes the recent conflict. So it plays the same effect as the forgetting policy. And this ink has also some heuristics to update it to control its limit. Now the score of variables in conflict clause are bumped with ink. And recently in the Maple solver, in recent about 5 years earlier, the score of variables related to the conflict analyzed are also bumped with half of the ink. So what variables are related to this conflict? That happens when we do the conflict analyze, all variables that involved in the analyzing procedure, they are considered to related to this conflict analysis. And for these variables, although they do not directly appear in the conflict clause, they have also a relation to this conflict. So their score plus half of the ink. Okay, now let's look at the learning rate-based branching heuristic, which is used in the Maple solver in 2016. In this version, in this heuristic, the score is computed by a formula as this. So 2 parts. The first part, this is the current score, and then this is the update formula, right? So we use this prime to show that it's the current value, and then after this update, this is the updated value. So this formula, we have a proportion from the current value, and then another proportion from the later part. What does this later part mean? Let's look at the formula. Li actually is a measurement of the number of learned clauses during an interval of time, and this interval time I is the interval between the assignment of V until V transitions back to being unassigned. So here we focus on a period. We focus on a recent period about which is related to this variable. And then when we focus in this recent period, we count how many learned clauses V participates. And this is PVI. Okay, and this AVI here is the reason sign rate. This PVI, if PVI counts the number of learned clauses where V participates, and AVI here counts the number of learned clauses that V involves in the conflict analysis. Okay, so together, this sum counts the frequency in this period, the frequency that this variable V participates in recent conflicts. Then we can compute this together to update the score of V. Now this is the LRB heuristic. And VMTF is the simple version of VMTF is just a priority queue. When we meet a conflict clause, then we move the variables in this conflict clause to the front of the queue. Then next time when we branch, we just pick from the front of the queue. Okay, after we pick a variable, we need to decide which value to assign this variable. In the early days, we have all zero before 1 or 1 before 0 or just random. But after 2007, the phase saving technique is proposed. Simply, this phase saving technique says that when we backtrack, we just save the assignments for this path to the for this current path, and then after we backtrack, we will continue the CDCL search. Then next time when we pick the variable to branch, we just simply assign the previous assignment. Why to do that? Because when we backtrack, for many variables, their assignment will be erased, right? And then we need to decide again which value to assign to this variable. But we discovered that actually, when we backtrack, the formula can be divided. The formula may contain different components, and they have no relations. For example, in this picture, suppose we begin from decision level 0, and then here we miss a conflict, and suppose the conflict analyze let us backtrack to level 1. Okay, but in this procedure, the variables compose the two connected components, and these two components are disconnected with each other. So the reason of the conflict analysis here should not have effect to these components, and we erase all the values here is unreasonable. So in this intuition, the phase saving proposed to remember all the assignments before backtracks, and after we backtrack, if we remember all the assignments, suppose 0, 1, 1, 0, 1, 1, 1, and after we backtrack in the branching, when we pick a variable to branch, we simply use this assignment to branch. But later we found that this should be cooperated with some phase resetting. Otherwise, it will too focused in some assignments. Besides the heuristics for decision, for branch and phasing decision, we also need to manage the clauses, the learn clause, because during the CDCL search, we learn more and more clauses. And if we do not reduce the clauses, the number of clauses will increase to a very large number, and that will make UP very slow. Also, not all of the learn clauses are helpful in the future. And to manage the clauses, we get an important breakthrough is the LBD. Before that, we just use the LRU heuristics. This recently used. Simply discard clauses that are not involved in recent conflict. But in 2009, the LBD heuristic is shown to be much better than LRU. This LBD counts the number of different decision levels in learn clauses. And a clause, the quality of a clause is measured by LBD. Generally, the small LBD implies that the quality of the learn clause is good, is better, and the clause should be kept in the near future, should be useful in the near future. And the modern version of this LBD involved three-tiered clause management. This is in O's paper in the SAT conference 2015. The three-tier divide the learn clauses into 3 tiers. In the core tiers, we have the clauses with LBD smaller or equal to 3. And these clauses are considered the most important. Okay, in the middle, we have some clauses with LBD smaller than 6. They might be useful. And the remaining parts are called local, the local tier. And this 3-tier method is dynamic. The first rule is that the core tier never be removed. Any clause with LBD smaller than 4, it stays in the core and never be removed. And periodically, we update the tier. Half local clauses, we remove half of them based on the score. So some of them will be discarded. Also, periodically, we move some clauses in the middle tier to local. If in the middle tier the clauses recently not used, then they will be degraded to the last level, to the last tier. And also move clauses encountered in local many times to middle tier. This is an upgrade. If a clause in a tier encounters is useful many times, then it is moved to the better tier. And also happens in middle to the core. So in nowadays, almost state-of-the-art CTCL solvers are based on this 3-tier method to manage the learned clauses. And CTCL is also
Hi, Troy. Yeah, I have a question. I saw this 3-tier clause. Can you hear me?
Yes.
Yes. So for this 3-tier method, so we have the experience like the number of the core clauses will not increase dramatically because we didn't delete these core clauses. We never delete them.
Sorry, you have an echo.
Can you hear my question?
Sorry, you have an echo there.
Can you hear me right now?
Yeah. Now it's clear. Now it's clear.
Yeah. So in this 3-tier method for the clause management, we never delete the core clauses. So it means that we have the experience that the number of the core clauses will not increase dramatically during the solving.
Yeah.
We have the observation.
Oh, you have this observation in your experiments?
I mean, do we have this observation that the number of the core clauses will not increase dramatically?
Yeah, in the paper it shows that. Also, we have the dynamic updates. If some for this LBD smaller than 3, the proportion is not very large. But I forget the detailed proportion is not very large.
Oh, the detailed.
Yeah, I can check the. I can check the literature and maybe you can send me email and we check later. I'm not sure the details, but we have seen some experiments that this number is a small proportion. It is not very significant. Can you hear me?
Yes.
Yeah, I think that answers Jiyoung's question. He's just having some echo problems. Yeah, we can probably move on.
Okay.
Yeah.
Okay. So in the previous algorithm we have seen, we assume that the algorithm is a tree, right? Is a search tree of the partial assignment. But actually, modern CTCL solvers employs frequent restarting. So it actually looks like a forest like this. And it has been shown theoretically that if we combine cross-learning with such restarts, that theoretically correspond to a proof system as powerful as general resolution and is stronger than DPLL proof system. So this also explains the much better performance of CTCL than traditional DPLL in theories. And also many evidence have shown that when together with cross-learning, the restarting is very important. It can be practically effective. And for restarting, we have two main policies. The first one is the Ruby series, which not only apply to SAT solvers, but also to other combinatorial problems, and is from some statistical principles. So it goes like this: 1, 1, 2, and then 1, 1, 2, 4 in an exponential growth. Then, but each round we begin with 1, and then 1, 1, 2, and 1, 1, 2, 4, 8, and then still 1, 1, 2, and 1, 1, 2, 4, 8, 6, and then so it has some theoretical guarantee. In glucose restart, it's rapid. Interesting, when the Ruby restarting policy is applied to SAT solvers, at that time people called it a rapid restart. But nowadays, compared to glucose restarting policy, Ruby actually is quite stable. Glucose restarting is much rapid. This restarting policy restart the algorithm when the average LBD is greater than the average of LBD of all length crosses. So it depends on the distribution of the length crosses. And experiments show that glucose restarting is much frequent. And an important observation in recent years, in 2015, is that Chen Xiao, he did some experiments and he found that glucose restart generally is useful for solving unset formulas, while Ruby series is Ruby restart is useful for solving SAT formulas. So he gave a conjecture that rapid restarts generally helps in deriving a refutation proof, while remaining in a stable mode is better to find the model. So in his work, according to this conjecture, he proposed to interleave between stabilizing mode and focused mode. In stable mode, we do not restart, so we just keep the search stable in order to find a solution. And in the focus mode, we restart quite a lot because it has been shown that for solving unset problems, frequent restarting is helpful. And now many solvers also interleaves between these two modes of restarting policies. Okay, now I will also mention clause simplification. When we learn the clause, it might contain many literals, and we try, on one hand, we try to discuss some length clauses, right? And also, we consider that we want to shorten the length clauses. When we learn a clause, we try to simplify it. And one way to do this is to do the to consider the implication. For example, here we length clause corresponds to this cut here. Then this length clause is x10 to true and x4 to 0 and x11 to 0, right? Corresponds to 3 literals. And in this graph, in this implication graph, we found that there is a connection between x10 and x11. If x10 is assigned to 0, then we can imply that x11 must be 0, or on the opposite. So there is redundant information in this course. So we simply drop x11 here, because once we get the information of x10, we can the value of x11 is already decidable. It's already decided. And we have the general version. In this version, we consider 2 literals, their implication relation. But we can consider more literals. If we learn the clause, we learn the clause, and in the clause there are some literals together can imply another literal. Then we can also drop the implied literal. Okay, there are many other things about CDCL and pre-processing, the technique used in pre-processing and in processing. In processing is also a technique in CDCL, but I have to move on. And parallelized set solving about the cube and conquer, especially this one, and also portfolio and incremental set solving is to deal with a series of set instances where each formula is modified from the last one. But I will now move on to the local search part. Local search is another main method for solving set. Compared to CDCL, local search is quite simple. Actually, is in an engineering way, it's also like it. It works in the complete assignments. We remember that CDCL works in the space of partial assignments, right? But local search, they works in the space of complete assignments. We can see the 2 to the power n assignments as a network. So all of the possible assignments, they are organized according to some relation. They're organized to a supercube, to a network. And then the local search actually starts from one point of the network and then go to another one and take a random walk in the network and trying to touch a point corresponds to a solution, okay? So in the algorithm, this local search method begins with a complete assignment. In the beginning, we get a complete assignment. This can be randomly guessed, or we can employ some greedy heuristics to assign, to get the values of the variable. And then in each iteration, we modify this complete assignment step by step. And typically in each step, we just pick one variable. We just pick one variable and change its value. And this corresponds to jump from the current point to the neighboring point. And the word local comes from the fact that this kind of algorithm can only see a local viewpoint. If it sits in the current point, it can only know its neighbors, the information of its neighbors. And it will forget where it has visited. These are the basic concepts of local search. We have the search space, which consists of all complete truth assignments. And in this search space, some of the complete assignments are models, are solutions. Then we need to introduce a neighborhood relation. This is algorithmic. We can define different neighborhood relation, but typically now local search algorithm use the Hamming one, the Hamming distance one. Hamming one, which means that only one variable has different value. And by using this neighborhood relation, we can organize the space of the complete assignments into a network. Then how to get a search to work in the network? We need a function to evaluate the quality of each point in the network. For example, we can define a function as the number of unsatisfied clauses under the given assignments. Now we get the evaluation function. So suppose we add the current points and we have several neighboring points. Each point corresponds to a complete assignment here. And the very simple algorithm can be like this. We pick the neighboring point with the best evaluation function and then jump to it.
Shall we? Yeah, I think now we can see the screen.
Okay.
Oh, yeah.
All right, continue.
Yes.
Okay, I will go a little faster.
So shall we, I mean, you mentioned that you start off with a complete assignment. Is it a random assignment or there is some way in which you choose the initial assignment?
You mean in the initial assignment, right?
Yeah, the initial assignment.
It can be randomized, but it can also be in a heuristic way. Hello?
Okay. Yeah, but I guess the heuristic has to be very fast, right? Because
yes, it must be linear or some very fast. Yes.
Okay, sure.
Okay, so in local search, the two pillars, scoring function and search strategy. In the concepts, we introduce evaluation function to evaluate the complete assignment. But actually, when we implement the algorithm, we actually use the instead of using evaluation function, we actually define the scoring function for variables, which measures the benefits of flipping a variable. Okay, so for example, we have a scoring function named score, and score x equals gs minus gs plum, where this differs from s only in the value of x. So this is a scoring function. So in the real practical local search solvers, we use scoring functions rather than evaluation functions. For example, in this small formula, let's say we start with a complete assignment or 0. And in this assignment, we have unsatisfied clauses. We have 2 unsatisfied clauses. And then we, using the Hamming one neighborhood relation, we have 3 neighboring, 0, 0, 0. Then we have 3 neighbors, right? We can be 0, 0, 1, 0, 1, 0, 1, 0, 0. Then each complete assignment have a evaluation function. For example, defined as the cost, the number of unsatisfied clauses here. Then for variable x1, we can define its score as the value, the cost of the current assignment and the cost of the assignments we obtained if x1 were flipped. Then in this way, we can calculate the scores of all the variables. Then we pick we can pick the variable according to these scores. So in this example here, x1 and x2 looks better than x3 because their score is larger. The larger score means that the are better benefits. Then this is the first local search algorithm for sets. The first one, but actually in 1991, similar local search algorithm and some very simple has been approached, but this one is the first famous one. It's called GSAT. It is famous because in the history, at the time it was approached, it outperformed the DPLL on several benchmarks of NQs and some combinatorial problems. This algorithm is very simple. It starts from a randomized initial complete assignment. Okay, here it's a randomized, and then with a loop. Usually this is given by some time limit. Okay, for example, some step limit or time limit, and in each iteration, first to check if the current assignment is a solution. If yes, that is very happy, and otherwise we pick a variable. And in GSAT, the variable is picked according to the best score, the highest score, and then you flip this variable. So it's simple, right? It's very simple, but the performance is good. And then in 1993, the seminal paper and the former paper is 1994 in AAAI. Selman and Henry, they proposed this walk set, also known as focused random walk. In this type, it's actually a random walk algorithm, and it's focused because it only focused on unsatisfied clauses. In each step, you first choose a random unsatisfied clause. And then one of the variable in this chosen clause is randomly selected and flipped. And this is not uniformly random. Actually, you can use some heuristic here. And in the original walk set, it is like some 3 tires. If there exists x, which does not lead to additional unsatisfied clauses, it is picked. So this is called a break x is 0, it is picked. And otherwise, if property pick the minimum break value, pick the variable with the minimum break, and else just random. But the framework here about first choosing an unsatisfied clause and then choosing a variable from this clause is called focused random walk. And it represents a family of local search algorithms because in each time it focuses on the unsatisfied clauses. And besides the two framework, there is a significant line in local search for sets, which is called cross weighting, constraint weighting. The principle is that to emphasize the importance of the clauses that frequently being unsatisfied. So this method can date back to the breakout method in 1993. Each time it reached a local optima. A local optima means that in the current assignment, all its neighbors are worse than the current assignment. So we can find a better way to go. So this is a local optima, and this method says that when the algorithm touch a local optima, it increase the weights of each unsatisfied clause. Note that in the original SAT problem, we do not have weights, right? So these weights are introduced by the algorithm to change the scoring function. A modern cross-weighting usually have a smoothing mechanism. Actually, it's somehow like forgetting mechanism. It's similar to the branching heuristics in VSIDS because the cross-weighting decision made in earlier history cannot be considered as important as nowadays, as the current stage. So we need to forget some of the weights. And here I list some of the typical weighting method here. The discrete Lagrangian method, you follow the breakouts to increment the scheme, but additionally, after a constant amount of increases, you will decrease the cross weights. And the PAWS in 2005, it also works similar to DLM. And okay, I cannot go into this so much details, but another type is to update the weights by multiply them with a vector. And in this, we have two schemes here. In the first scheme, after reaching a local optima with some property, for each cross, the weight is pulled to the average weight, right, by this linear formula. And we have an average weight here, and some is higher and some is higher and some is lower. But by using a linear combination, all are pulled towards the average value. And this one depends on a threshold, SWT. When the average weight reaching a threshold, then we smooth the weights. And now here it is a independent parameter in this scheme. So in nowadays, many local search algorithms use cross-weighting to change the scoring function. And now we go to the scoring functions. We have the basic function, the score we have already seen. Score equals the cost of the current assignment minus the cost of the assignment that will be obtained if the variable were flipped. So this measures the change on the cost. And it can be separated into two components, the make and the break. The make property of a variable x considers how many clauses will become satisfied from unsatisfied. And the break measures how many satisfied clauses will become unsatisfied. So it is easy to say that, to see the score equals make minus break. And in the implementation level, important points in local search is that we should develop efficient implementation for calculating scoring functions. So depends on the framework. We can have catching or no catching. In the catching implementation, we first initialize the score. And in each step, we update the score. So in each step, if we pick a variable x, we only need to update the score of the variables y, which appears in the clause of x. Okay, so this is the clause set where x appears. Then we only need to update a small portion of the variables. And no catching usually is better for the random walk. Because at each time we just pick one unsatisfied clause, right? So usually the variable in that clause is not so many, so we can calculate it from scratch. And we can have more complex scoring functions, like we can have the age, the age measures the number of steps since X last change. And we can have the frequency, we can have the weighted version, we can have any mathematical expression with one or more properties, like an exponential polynomial type. And we can also have dynamic scoring function, which means that we can change scoring functions during the local search. And a recent typical method for scoring function is based on probability, which the very typical solver is proper set is also a random walk style. In each step, you select the unsatisfied clause and then compute the value of a function for each variable x, and then each variable x is picked according to the probability equals to this. So then the question is which function to use in this probability distribution. You usually use this A break X and break XA. So it's exponential and polynomial style. Okay, in about 2013, I proposed that we need to consider the satisfaction degree in the scoring function, because in the previous scoring function, we actually cares about whether a clause is satisfied or not, but we do not distinguish between satisfied clauses. I consider this is not reasonable. For example, consider this assignment. We have two clauses here, and both of them are satisfied. But they are satisfied in different strengths, right? Because in clause 1 we have four true literal, so it's very safe. But in the clause 2, one true literal, so it becomes in danger. It's a critical clause. So I propose that we should distinguish these two levels. Then I propose the second level scoring function to capture the critical case where the one satisfied clause, the satisfied clause with only one true literal, is a critical clause. So I propose the second level scoring function to measure the change between safe clauses to critical clauses, and this can be calculated in the same way, in the similar way to the score. And this can be used to break ties when several variables have the same score. We can pick the one with the bigger second level score, right? It can also override. You can also use to override the major score. For example, we have X and Y, and their score is very close. Suppose this is 99, this is 100, but their scoring, their second level score, suppose X is -1, it is 10, but Y is -10. Then in this way, maybe the second level score can override the priority. So then that we will pick X. So this is about hovering scoring function. We need to consider about the score and second level score. And this is more look ahead. It's more look ahead information. And the score is more greedy about the current state.
Shall we? Oh, one quick
Okay.
question. How hard it is to compute these MEC2 and BREC2 scores incrementally?
Yeah, we use a catching based, and it is about a small vector square, and this is about I remember a proportion about time consumption. When I add this to my CCA solver, this has about 12% time consumption.
Oh, wow.
Yeah. So it must be very helpful. Otherwise, the overhead is large, right? Yeah. So it's based on catching based calculation, and it's about a square complexity. Okay. So, but it really helps. It really helps for especially for case set with large k greater than 3. But for 3 set, we proved that this cannot be used, because for 3 set, any solution, the number of critical clauses is at least half of the clauses. So we do not have any reason to encourage a critical clause become safe. But for k greater than 3, this makes a breakthrough in local search for solving such formulas. And it's first used in the CCA SAT solver, which is the winner in the competition 2012 in random check. Okay, wow. And then the cycling problem. This is about the other main idea to deal with the main issue about local search, because as we say, local search is a Markov algorithm, right? It does not remember which paths it has visited. So you are revisiting candidate solutions, and this is no good. It wastes time, prevents from getting our local optima. And previously, we have some naive methods like restart and non-improving search, very naive. A famous mechanism for doing this is the taboo search in 1989, which is not only applied to SAT, but also many other combinatorial optimization problems. It simply forbids reversing the recent changes. For example, if we flip x from 0 to 1, then in the next t steps, it's forbidden to do this, to change x from 1 to 0 again. So now we know that this is a parameter. So the performance of taboo algorithm depends on the value of the parameter. And the other idea is the idea I proposed in about 10 years ago, called configuration checking. And initially that's defined to tackle graph problems, but eventually it comes out as a powerful technique for sets. And in this idea, we consider the circumstance of the variable. So a variable is allowed to flip only if its circumstance has changed since its last flip. So we need to, I will skip the taboo, okay? So because we don't have sufficient time. So I'm saying that this CC idea, this configuration tracking, considers the circumstance information. So how to define the circumstance information? Formally, this is defined as a configuration of the variable. Typically, we can consider the variables that has relations with the current variable. For example, for a variable x, then we can define its neighborhood as this. All right, we can define its neighborhood as all the variables that occur, that share clause with X, then this formed a circumstance. The values, the assignments of these variables formed a circumstance for X. Then with this circumstance definition, we can now describe the CC strategy. If for variable X, if its configuration has not changed since its last flip, then it should not be flipped. Here I have an example. For example, we consider the central variable here V, then we have red and black to represent 0 and 1 of the assignments. So it has 4 neighboring variables, and we have 0, 1, 0, 1. And in here, in some step, you change the variable we consider flipped from 0 to 1, from 0 to 1. And then after some steps later, we try to flip this variable again. Then we check its configuration. Now we discover that its configuration is different from the time it last flipped. So this is okay. It can be safely be flipped. And conversely, if when we try to flip this variable and we find that, oh, its configuration is just the same. It's just the same as the last time it was flipped. So it's when we flip this back, the local structure will be cycling. We cause a local structure in this part. So this is forbidden. And now, once we get the CC policy, we can use it to filter candidate variables. And we can also use it to give preference, to give a priority. This has already been used in many successful local sets and max algorithm. And also it depends on the efficient implementation. The accurate implementation is too naive and requires a high complexity. And we get an efficient implementation to lower it to a linear complexity. Okay, but this part explains that for random k-sets, this when does CC becomes ineffective? I try to answer this question and find a little bound, find a bound here for random k-set. And if we fix the ratio, for example, we fix the ratio near to the phase transition here, and only when this formula is smaller than 0, then this CC will become ineffective. It will become, actually it becomes trivial case. Trivial case means it only forbids one variable, so it becomes a taboo tenure, becomes a taboo method with taboo tenure 1. Then it becomes trivial. But this rarely happens. In this random case model, only when n is smaller than n star, it happens. And this n star is very small, right? So for a fixed ratio, a larger formula is more suitable to use the CC strategy. And in 2015, we developed a local search solver called CCNR, and currently it is perhaps the most successful local search for structured formulas. And it integrates several components here like CC and cross-weighting and and other stuff. And although also the focus random walk things here, but in the framework we have 2 modes. We have the greedy mode and the random walk mode. In the greedy mode, we try to find a greedy variable, according to the score or second level score, and using CC to do some filter. And after we get into the local optimal, we use a diversification mode. Actually, we update the crossways and do our random walk. But in the random walk mode, we still get the greedy variable. And this is important. This is important for solving structure formula. Okay, eventually we find to the final part. I hope I have some time to finish it. We already introduced two methods, CDCL and local search. They are very different, as we can see. In the history, in 1997 IIII conference, but Selman, Henry Coase, and David, they proposed 10 challenges in propositional reasoning and search. And the seventh challenge is that can we develop a new algorithm that outperforms both DPLL-like and local search-like algorithm by combining the advances. And this has attracted many interest. We have different types of hybrid solvers come out. And the first one type use a local search as the main body and try to integrate the techniques in CDCL or DPL into local search. We have some works here. We have hybrid GM and use CDCL as processor resolution in local search. The second type use DPLL or CDL as the main body and use local search to solve the sub formula or to activate local search at each node of DPLL. And the recent progress is Calico and KeySet. It calls a local search procedure when do the replacing, but it is used only once immediately after the local search process. And there is also naive combination about local search and CDCL. We can first call local search and then call CDCL, or on the opposite, we first call CDCL and then local search. It's more like a portfolio. So this is not more like a portfolio. A turning point in this hybrid solving, personally, I believe the turning point happens in about 2011 or 2012, because before that, it has been longly believed that local search is only good at solving random formulas, and CDCL is powerful at solving structure, especially industry formulas. So it's difficult to use local search, try to improving performance on industrial formulas, right? This is a very long belief. But in 2011, nearby, after that, we have some modern local search solvers. SAT in 2011, proper SAT in 11, and CCNI in 15, and also YASET. And in the competition, particularly in competition of 2011 and 15, 14, there is a benchmark crafted, and later on, afterwards is called hard combinatorial. And in this benchmark, local search has been shown to very competitive. Sometimes can solve many, can solve some instances that all CDCL solvers cannot solve. And then people find that actually the performance of local search, the comparison of local search and CDCL on the benchmark actually depends on the people submitting benchmarks to SAT competition. And if we look outside the competition, we can find some typical examples where in the industry where local search can performs better. For example, in FCC projects in USA, they try to allocate resources in the resource allocation projects, real projects. And there are two core solvers there. One is a variant of CCS and the other is a variant of glucose. And it was shown that the local search solver performs the best in this industry benchmark. So this is somehow surprising. And also we have found some other examples later on. For example, in the software texting, and Manai showed that some local search solvers can be better than CTCL in the matrix multiplication, and also some other mathematical problems have been shown to be solved by local search solvers. So in 2015, when people realized this fact, they simply put local search and CTCL as a sequential portfolio and participated in the hard combinatorial check. And as we can see, the winners of that check all belongs to hybrid solvers that combine local search and CTCL. And this fact has been emphasized also in SAT Challenge 2018. And here they count the margin contribution, which measures the contribution, the number of instances or the contribution of a solver contributes to the benchmark that it can solve. If a solver can solve more instances that other solvers cannot solve, it will rank higher. So here the first one is a CTCL solver, and the second one is a hybrid, and the fifth is a local search. The seventh is also a local search. So we can see the situation here that local search and CTCL becomes complementary in industry benchmark, because here all the benchmark comes from the main track. And then afterwards, I try to combine local search and hybrid. As I can see, the problem is that local search and CTCL can be combined to develop more efficient solvers for industry benchmark. So that was very exciting. Now, at that time, I was thinking the power of CTCL mainly comes from the reasoning techniques, especially UP and cross-learning. So we try to apply these two techniques in local search, and we try several situations, and finally we find that by using UP in the initialization of local search can significantly improve the performance of local search. And a straightforward way is to doing like a branch in CTCL. We do a UP, and if we cannot do UP, we pick a variable and design the variable. And once we observe unique clauses, we do UP again until no more UP, and then we design again. And doing this to a complete assignment as the initial assignment, and then this can be used to improve local search. Okay, and this initialize the method is quite simple. Later on, we try to improve it by proposing a construct and cut method, a framework, because in the previous slide we just do one procedure, and it's linear time. It's a linear time to produce the initial assignment, but we just get one time. And I was thinking maybe we can do several times and pick the better one, but we need to save the overhead, so we can cut it. Each time we produce initial assignment, we can record its cost, and then we update the cost star during the multi tries. So some tries, when in the middle of the path, if it reach the cost star, it can be cut, right? And maybe some cut very earlier. And then after some multiple initial assignments, we get the best one as the initial assignments to the to the local search, and this can further improve the local search algorithm. Actually, I did this work in about several years ago, but the paper was just published this year. This approach was shown to be effective and generic for improving local search algorithms, including CCNR, proper set, and set time. And as we can see, for FCC, PTN, and SM5, the latter two are mathematical problems. And the first benchmark is a real-world industry benchmark. This CCNR plus CNC can be competitive to the state-of-art CDCL solvers. In some sense, it's better. Okay, but now previous versions only use UP to help local search. And then we try to, we have multi-trial of initialization. Can we use local search algorithm to feed back to the initialization? And according to this thinking, we develop another approach. In the initialization part, we still use the UP-based algorithm to provide a complete assignment as initial assignment, and then we do the local search within time limits. After the local search stopped and we did not find a solution, but we can provide the best found assignment during this search as a feedback to the second round. And in the second round, in generating an initial assignment, we can refer to this assignment in local search as a heuristic guide to the decision of the variables here. So this actually is more like the rephasing in CDCL here, but maybe we take it consider in different way. When the local search, the assignments are saved and be used in the construction. So following this way, we can improve the local search max set significantly. And for the first time in 2016, a local search algorithm won the industrial check. Okay, the second and the third ranking winner, they both based on set-based. They both on calling a CDCL solver, but this one is based on local search combined with the UP initialization and their cooperation. And then I was thinking, if we were to use UP to construct initialization, why not directly use CDCL to design an initialization? That should be more powerful, right? We can, in the previous slides, I said that we're doing UP construction and then to local search, and then local search feedback to UP construction. But this can be improved, that we can directly replace this UP construction by a CDCL. And now this comes to the recent work, did cooperation between CDCL and local search. So generally CDCL searches in the space of partial assignments, which makes it better to use reasoning techniques. But local search works in the whole space of all complete assignments. So actually local search can be better at sampling, but no better for reasoning. And according to the above consideration, I propose this framework that we plus a local search to a CDCL solver, and the CDCL solver produce a good initial assignments for local search. and then local search will search nearby. And if the local search fail to search a solution, it also does not waste time, because during this search, it can sample some information. For example, the local search assignments and some information about the variables, which can be feedback to CDCL to help boost the CDCL, especially the decision heuristic, like the branching and the phasing heuristics. So the first question is, we need to find a branch that can be used to produce an initial assignment for local search. Now, which branches deserve exploration? Our idea is that if a branch goes to a depth sufficiently large, for example, about half of the variables has been assigned, and the branch does not meet a conflict, and this is a promising branch, it's a good branch. Or the branch is going to a depth that alpha max is the top trail. Top trail means that it's the best trail in the previous CDCL procedure. And this is according to the history. And if we find a promising branch, either of the condition satisfies, we say it is a promising branch. If we find a promising branch, we can extend it to a complete assignment. How to extend it to a complete assignment? We just use the CDCL procedure to assign the remaining variables, but without backcheck. Even if we touch a conflict, we do not backcheck. We just go deep into a leaf. Okay. And in this way, we can go to a complete assignment and fit into a local search solver. And we need to limit the time of local search solver, otherwise the CDCL would be too slow. So we, in our first version, we limited to a certain amount of memory accesses, which is in this amount. And if the local search finds a solution that's happy, and otherwise you will return to the crop point and continue the normal CDCL procedure. So here after we run the local search, we can collect some information from the local search to help CDCL, right? And the first information is the local search assignments, as we already used in the construction and local search framework. When we run the local search procedure, we can collect the good quality assignments during the local search, and this can be saved as the phases to be used in CDCL. And now here the rephasing has been used in KeySet. In KeySet, it emphasized some lucky phase and random phase, and in a probability way. Here we also use in a probability way, but we in our paper here we show that all the set phases come from local search, and if we do the rephasing according to local search assignment, that is already very powerful. And okay, we reset the phases of all variables with local search assignments. And in the first version, in the SAT competition 2020, this is after each time CDCL is restarted, we do the rephasing with the local search assignment. But in this year, in the LS Tech Maple, the solver this year, this is due with a fixed frequency. And all the assignments here comes from local search, okay? Comes from the alpha max, alpha best, try to maximize the depth of the branch. And as the initial assignment, and the LS means local search. So we record the local search assignments starting from alpha max and alpha latest. Alpha latest is the latest local search, and best is the best local search assignments that we have found, because the local search procedure can be called multiple times during CDCL, and we record the best one, and this best one also plays an important role in the rephasing. Okay, finally, we can also improve the branching heuristics by the conflict frequency in local search. And this is about the conflict frequency. And there is a small story about this work, about this idea. In about 2019, Mete Sus visited me in Beijing, and we discussed about CDCL and local search. And I presented my work about CCNR and talking about cross weighting. And during our discussion, we talked about maybe the cross weighting in local search is somehow related to the score in VSIDS branching heuristics. So afterwards, we developed the ideas separately. So went back and we work on this idea. And finally, in 2020, we found that this similar idea has been used in both new tag relax and crypto mini set. And this is a cooperation between Sus and me and also Caldip and many other guys here. So the intuition is that CDCL is powerful owing largely to the employ of the conflict information branching heuristic. And this branching heuristic aim to promote conflicts earlier, right? So one question is that, can we use local search information to enhance branch heuristics so that it can promote conflicts? Okay, so to do this, we need to calculate some property of variables, and that can be used in the branching heuristics. Because in the branching heuristics, we actually calculate a score we calculate the score for variables, right? And we pick the highest score. So, and this score is related to the frequency of this variable involving in recent conflicts. And now, similarly, we can calculate our frequency in local search here. We calculate the frequency in this way, and during a local search procedure, we calculate how many steps the X appears in unset clauses. And this is divided by the total steps. This is the frequency the X participates in unsatisfied clause. And this will get an amount between 0 and 1. Then we multiply it by 100 to get an integer number, and this can be added to the score in VSIDS, or can be added to LRB can be added to the LRB score. And in both ways, we found that it can improve the performance of CDCL. So we use this hybrid method to improve 3 typical CDCL solvers, including glucose maple DL, the winner of 2019, and also KeySet. For KeySet, we only use the final idea, the conflict frequency, and then it gets a significant improvements. Especially, we have some bonus here. Here, the bonus means that for these formulas, the either the original CDCL or the original local search cannot solve such formulas, but they can be solved after combining the two types of solvers together. They can be solved by the hybrid solvers. So this essentially shows that by using local search information, we can indeed improve CTCL solvers, as we can see from this set bonus. And these better experiments are carried out on the main track benchmarks. Most of the formulas come from real-world applications. Okay, so finally we get some great results about our team, and all use the hybrid solver here. This also use the hybrid solver here. And this year we also use the hybrid method to SMT competition, and shows local search can be complementary to complete methods, and they can be combined together to get better performance. As we can see, this is an ongoing trend. The winners from recent competition based on hybrid solvers from combining local search and CTCL. All right, we finish.
Thank you. I think there have been questions throughout the talk, but we have some time for questions.
We have time. I thought.
Well, we can still have some questions.
Okay.
So
shall we? Yeah.
Mm-hmm.
So there is also some, I don't recall if you mentioned, there's some work on using machine learning kind of techniques, right? To decide. I mean, do you? I mean, do you
Yeah.
think that? Yeah. So do you think that you know, the kind of scores that you're getting, the kind of what you just showed, is using local search to sort of.
And this score here, branching score here. You mean we can develop machine learning to help develop scoring function?
Right? I mean, I don't think they performed very well, but there was some work related to that, right? Earlier.
Yeah.
So
actually, this LRB, they use a multi-armed learning technique, but according to the literature, a better way to do this is we have several branching heuristic, and then we use a learning model to pick which one to perform. This seems a promising way, but I did not see a good example to learn a branching scoring function from empty. I did not see an example of that yet.
Okay, sure.
So I think I also wanted to ask a similar question, which is, what are your thoughts on coming up using graph neural networks or something similar to some machine learning techniques to come up with the scores? Because they might be capturing the structure in the formula.
You mean from scratch? No any guidance from people?
Not from scratch, but during solving, can we use can we represent the formula using a graph with the current state, and then try to come up with scores based on graph neural networks? I mean, there is some work on graph neural networks and trying to predict. Do you see some use of it in guiding the local search solver?
We have one work in last year in using neural network to producing initial assignments. Yeah. So, and it can be useful for random benchmarks.
Okay.
Yeah, it's called N local set. Never.
Okay,
Yeah.
right. Are
But
there-
for CDCL, yeah, I haven't seen examples for learning scoring functions for CDCL. Maybe it's interesting direction.
yeah.
I show you.
Hi.
So we know that local search solver now performs well on random benchmarks and also on some specific structure benchmarks, right?
Yeah.
So if we know that with high confidence that an instance is satisfiable, can we expect the local search solver performs better than CDCL solver?
Well, that actually that still depends on the specific structure. For example, we found that if the formula has a structure similar to the graph coloring problem, usually local search performs better. So many mathematical problems, according to the recent literature, can be tackled better by local search. So that depends. I think that depends on the domain.
I see. And also I noticed that we have seen the local search performs well in the matrix multiplication, right? So did you try local search with some encoding of the neural network? Because a neural network is similar to matrix vector multiplication.
We haven't done that. Yeah, you mean using local search to help the neural network?
Yeah, to do some encoding of some binary neural network outside.
No, not yet. I guess to verify the neural network, they must use a complete solver.
Yes, but in some application, there must be a lot of solutions for neural network, for some instance of neural network. And
yeah.
Hope the local search will perform well in that benchmark.
That's interesting. Yeah.
Also, I have a question about the algorithm for local search. So when you reach a local optima, what will you do? You will restart from a different initialized value.
Usually we'll just do some perturbation. For example, some random walks. Yeah.
It's like add some randomization to this searching process.
Thank
you.
So, sorry.
Hi.
In case of SAT solving, so we differentiate the part when we are trying to look at it as a satisfiable instance and unsatisfiable instance. Like
which page?
Oh, so like the modern SAT solvers, they have two pages generally. When they look at the instance as a satisfiable instance and tries to solve it with some different strategy. And in some cases, they try to solve it as an unsatisfiable instance, right?
Yeah.
So, like Chance-O's strategy. And this local search, they kind of looks at the instance as a satisfiable instance. So do you do different strategies for SAT and unset pages when integrating this local search with CDCL? So
you mean in the experiments, the benchmarks? Are you talking about there are satisfiable benchmarks and unsatisfiable benchmarks, and you?
No, not really. So I'm trying to reiterate the question. So the modern SAT solver has two pages generally. One is the SAT page, and another is the unsat page. Right?
Yeah.
So I think like the local search should be helpful in satisfiable phase and not in
Yeah.
unsatisfiable phase, right?
Yes. So here, yes. I forgot to mention that here the improvements was made on the as you can see now, we have the set number and unset number, but the improvements was made bias the satisfiable parts.
Okay, yeah.
You know? Yeah.
Okay. So in case of
but
unsatisfiable page, do you not use this local search integration, or do you use that in that part also, like the replacing?
But in solving a problem, we do not know whether it is satisfiable or unsatisfiable. So we have to, and maybe if it is an unsatisfiable formula, this local search help, except the last one, this conflict frequency, it was found, for example, here in 2015, the key set said that the answer number is 98, and plus conflict frequency can be improved to 104. But many of the time, the improvements was only limited to satisfiable parts.
Yes. Yeah. Thank you.
Thank you.
All right, I guess we are well over time, so probably we should at least officially end the session, and we can continue discussions on Discord if there is interest and if there's time. Thanks a lot, Shavi, again for an excellent tutorial. All of us really enjoyed it. Thanks for taking all the questions. It's been long, 3.5 hours. 4.5 hours. So we are really grateful for it. With that, we do have the Discord channel, so I invite everybody to move there, and I hope if Shavi will be able to stick around for some time at the Discord channel. But with that, we are coming to the end of this year's edition of the SAT+SMT Winter School. I will let Supratik close the school officially.
Yeah, thanks, Kuldeep. Thank you, Shavi, very much for very nice tutorial, very insightful. And I would like to, basically conclude the winter school by thanking our sponsors, which is Tata Consultancy Services Research, and also the Indian Association for Research in Computing Science, IARTS, which provided the all the logistical help for getting this workshop, getting this winter school going. And of course, big thanks to all the speakers and the audience for staying around and participating in the discussion. So thank you, everybody, and we look forward to seeing you again in next year's edition of the school. Thank you.
Thank you.